Hello, this is Gregory Maxwell, and in this lesson, we will talk about solving exponential and logarithmic equations. Solving exponential and logarithmic equations. And a large number of the slides that I'll be using in this presentation are from PowerPoints produced by Professor Shauna Hayder at Salt Lake Community College. Let's get into the topic for today. Now, to do this, we need to remind ourselves of a few concepts from exponential and logarithmic functions and their properties. Namely, first of all, the definitions. An exponential function is a function where the variable is in the exponent and the base is a positive number other than 1. A logarithmic function is the inverse of the corresponding exponential function with the same base. Therefore, if you're trying to convert between the two, you look for the base first, and then the output of one becomes the input of the other, and vice versa. So a logarithm is really the exponent of an expression. You have an expression, a base raised to a power, and then you get the answer. That power is actually what the logarithm is. I encourage you to check out my other video on the properties of logarithms for more details. Based on that understanding of logarithms, if I say log base b of b, I mean b to what power gives you b? That power is 1. That exponent is 1. So log base b of b is 1. Log base b of 1 is 0 because any non-zero number raised to the power of 0 is 1. And b is a positive number other than 1. That's a requirement for the base. Since logarithms and exponential functions are inverse of functions, then when you do a composition of one with the other, you only get the input. So log base b of b to the x is just x, and b to the log base b of x is x. More explanations in the other lesson. Logarithms, when the base is base 10, is just written as log. So when you see log without a base indicated, that's base 10. And ln is the log with base e, the logarithm of base e, known as the natural logarithm. The rules and properties of logarithms comes from the rules and properties of exponents. So the log of a product is the sum of the logs. The log of a quotient is the difference of the logs. And if you find in the input of a logarithm is raised to a power, that power can become the coefficient. So that's the product rule, the quotient rule, and the power rule. Those rules work both directions. If you go from one direction to the other way, you produce a wider number of logs. That's called expanding the logarithms. But if you're condensing them in multiple logs into one, that's called condensing the logarithm. I'd like to just have you look at those errors that you should avoid on the right-hand side. I won't go through them all, but those are common errors of people trying to evaluate or use the properties of logarithms. Be very careful of that. And then the next property of logarithms I want to remind us of is the change of base property, which says you can change the base of a logarithm to any arbitrary base, any arbitrary legal base you'd like to use. All you have to do is do the logarithm of the input over log of the output, where the logarithm is of the new base. So for example, if you want to change to base 10 and you have log base b of m, you can just do log of m over log of b. If you want to do a natural log, you can just say ln of m over ln of b. And that's indicated at the bottom right here. And another property of logarithms that also has similar conditions for exponential functions is that they are one-to-one functions. Functions means if you plug in the same number, you will always get the same result. One-to-one means if you get the same result, it's because it's the same number you plug in. In other words, in a one-to-one function, if you use two different inputs, you will get two different outputs. So if you plug in two numbers and you get the same result, those two numbers have to have been the same for this function to be a one-to-one. And that now, with those properties of logarithms, those allow us to be able to solve logarithmic and exponential equations. We'll start by talking about solving logarithmic equations, and then we'll talk about solving exponential equations. Now, generally speaking, when you're trying to solve a logarithmic or exponential equation, you try to simplify the expression by trying to get the variable by itself as much as possible by using the reverse of the PEMDAS. Please excuse my dear Aunt Sally, as the summary says, parentheses, exponents, multiplication, division, addition, and subtraction, which is the order of operations. And that's from basic algebra and pre-algebra. So we're trying to get the variable by itself by doing the reverse operations. And remember, the weakest links in the PEMDAS in the order of operations are addition and subtraction, and they are inverse operations of each other. The next weakest are multiplication and division. Those are inverses of each other. The next weakest is exponents, which the inverse of exponents is radicals or roots. But in addition, we can rewrite exponents now as exponential, as logarithmic functions, and vice versa. And then the strongest thing is parenthetical terms. So we'll do a few questions like that as we go along. The first type of logarithmic equation we're going to solve here are the simple ones where you have a basic log equal to a number. What we do is we try to get the variable by itself, and when we get stuck, we convert that equation into exponential form, then solve for the variable. And remember now, after you solve, you need to check your answers to make sure they are legitimate answers. And always check based on the original equation that you're given, and whatever equation doesn't produce what you're looking for, you need what doesn't produce a variable that causes a positive input to a logarithm, then that variable is not a solution. Let's do a few examples here. Let's say we're trying to solve this equation, log base 2 of 2x plus 1 equals to 3. We're trying to solve for x, and there's no way for us to isolate the x anymore. So what we're going to do is convert this logarithm this equation from a logarithmic form to an exponential form. Since we're going to convert to exponential, we look for the base. The base is base 2. The output was 3. That becomes the input, which is the exponent, and the input becomes the output. So we end up with 2, which is the base, to the power 3, which was the output, now becomes the input, is equal to 2x plus 1, which was the input and now is the output. This becomes a simple equation to solve, and all we have to do is work out 2 to the 3, which is 8, and solve for x. And there we have it. X is equal to 7 over 2, or 3.5. To see if we're correct, we plug in to the original equation. We do 2 times 7 over 2 is 7. 7 plus 1 is 8. And log base 2 of 8 is indeed 3, because 2 to the 3 is 8. And there we have it. Now, let's do a few more examples here for ourselves. Let's solve these equations here. So we have this equation, log base 5 of x is equal to 3. Very simple. We're trying to isolate the x. So we simply rewrite this equation in logarithmic form. 5 to the power 3 is equal to x. And that's our answer. 5 to the power 3 is 125. And that makes sense. Log base 5 of 125 is 3, because 5 to the 3 is 125. Now, if it's ln, then your base here is e. So you should be thinking of this as log base e of x. We don't typically write that, but that's what it means. So when you're solving this, then that means x would equal to e to the 3. I'll write that down. E to the 3 is equal to x, or x is equal to the cube of e cubed. And that's that. And since I'm only looking for exact answers in this part of the exercises, we'll just leave that as an answer. E is an irrational number, so we can only give an approximate number otherwise. In this case, we have log base 5 of x minus 7 is equal to 2. We'll rewrite this in exponential form. So the base is 5, so 5 squared is equal to x minus 7. The square comes from the equal. The 5 expression is equal to 2, the output. So 5 squared is 25. And so now I just simply solve for x. 25 plus 7 is equal to 32. And that's our answer. And as always, we can check our answers. We plug in 32 here. 32 minus 7 is 25. Log base 5 of 25 is 2. Then for this one, we're going to solve by first getting rid of the weakest link, which is divide by the coefficient of the logarithm. So I'm going to divide by 6. And when I divide both sides by 6, I get natural log of 2x is equal to 5. Then I will rewrite this in exponential form. Since this is log base e, I write that as e to the 5, and that's equal to 2x. And then I just divide both sides by 2. So the answer is e to the 5 over 2, or half e to the 5. And there we have it. And again, you can always check that. I'll leave you to check that answer. You can use a calculator as well. Now for this one, this is very similar to the one we did up here. So our pattern is basically the same. We have 2 to the power 5 is equal to 4x plus 1. 2 to the 5 is 32. And then you just subtract 1 and divide by 4. So that's 31 over 4 is our answer. So x is equal to 7.75, or as I prefer to put it as an improper fraction, 31 over 4. For this question here, we're going to have a logarithm of a radical. No problem. ln means log base e, so I just do e to the 1 is equal to the square root of x plus 4. I want to get rid of that square root, so I'm going to square both sides. So I'm going to square the right side here, which will cancel the radical, and the left side, which will just give me e squared. And then, so we have e squared is equal to x plus 4. I subtract 4 from both sides, and x is equal to e squared minus 4. Finally, in this exercise set here, we'll have this equation. Very simple. We get rid of the weakest link, subtract 7 from both sides, so we have 3 ln of x is equal to -1. Then I divide by 3, so I get ln of x is equal to -1/3. And then I take I realize that log base e is ln. I also can do something like this. I'll just write both sides as exponents of e. It's the same process as what I was just doing. So it's actually an additional step, but it's just illustrating something else that can be done. So this gives you x is equal to e to the -1/3, which is 1 over e to the 1/3, which you can then say that this is x is equal to 1 over the cube root of e. The cube root of e. 1 over the cube root of e. And there you have it. Feel free to go back through these slowly, step by step. And now we'll talk about solving logarithms using the one-to-one property. If you have a log equal to a log and both of them have the same base, then this becomes an even easier process. It's a one-to-one property. If the log of m is equal to log of n and both logs have the same base, then the inputs must be equal to each other. Must be the same. So as always, we still need to check to make sure that we are doing the right operation, that we are getting the correct solutions here. So let's do a few of these quick examples here. First, we need to make sure that we have a log of an expression equal to a log of expression, and the logs must be of the same base. So in this case, the base is both 5, so that means the inputs are equal. So we have 2x plus 3 is equal to 3. I can just now solve that equation very simply. Subtract 3 from both sides, and then divide by 2. So x is equal to 0, sorry. And then let's do a quick check to make sure that we are correct. I'm going to plug in 0 for x, so I get log base 5 of 2 times 0 plus 3 is equal to log base 5 of 3. And that gives me log base 5 of 3 equals to log base 5 of 3. And so both sides work, so that means this is my solution. With the next question here, we do the same thing. I can approach this one of two ways. I can multiply both sides by 2 to get rid of this half, and then proceed from there, or I can make both sides exponents. I'm going to choose the first option. So I'm going to multiply both sides by 2. and I end up with log base 3 of x is equal to 4 log base 3 of 2. Then I still have a problem where one of these still has a coefficient, and I need both logs to have no coefficients in front. So I'll use the power property to move the coefficient to be the exponent of the input on the right hand side. So now I have log base 3 of x is equal to log base 3 of 2 to the 4. It means then that the inputs are the same, x equal to 2 to the 4, which implies that x is equal to 2 times itself 4 times, which is 16. And then you can check that by saying log base 3 of 16 equal to 2 times log base 3 of 2. Well, you can check those on the calculator. You will see that those, when you plug those in, both sides work out to be the same. Alternatively, you could say half becomes the exponent of 16. So 16 to the half is the square root of 16, which is 4. So the left side is log base 3 of 4. And the right side, if you move the 2 to the top, that becomes log base 3 of 2 squared, which is log base 3 of 4. Same deal. In this one, instead of dividing both sides by 2 to create another fraction, which will be a little bit more tedious, what I will do is make both sides exponents. All right, so on the left side, we have log base 5 of x squared is equal to, on the right side, log base 5 of 4 cubed. Now, since the bases are the same and we are talking about log equal to log, one-to-one property says x squared is therefore equal to 64. You take the square root of 64, you get plus or minus 8. But we cannot use the negative value because when we try that in the original equation, you will be plugging in the logarithm of a negative. So that doesn't work. But the positive does work. So the solution then is 8. Only 8 works. So I just put a little quick note here on the side, that note log base 5 of negative 8 does not exist. So the only answer that works is positive 8, and when you check it, you'll see that both work. Let's continue down here for question number 4. Question number 4. Where we have the same situation, we need to make that exponent. We have to make that exponent, that coefficient into the exponent. So we have log base 4 of x to the negative 2 is equal to log base 4 of 9. Then this means x to the negative 2 is equal to 9. And this is a very interesting thing here. This, if I multiply both exponents, you'll see that it works out that way as x to the negative 2, x to the 2 equal to 1 over 9. Alternatively, I could rewrite this way, x squared is equal to 9. And then I rotate the reciprocal of both sides, I get x squared is equal to 1 over 9. And then if I do the square root of both sides, I get plus or minus 1/3. And as before, only 1/3 works because we'll be finding log base 4 of negative 1/3 does not exist. However, if we did do log base 4 of 1/3 here, that will still work out pretty nicely. You'll see, you can check that one. Let's go on to this example here. We're going to do the same as we did in the previous example. Move the coefficient to become the exponent. And in this case, we have to move both coefficients to become exponents. So we end up with log base 2 of x cubed is equal to log base 2 of 27 to the negative 1. The bases are the same, log is equal to log, so inputs are equal because that's one-to-one property. I'll rewrite 27 to the negative 1 as 1 over 27, and then I will find the cube root of 1 over 27. And of course, that's the cube root of 1 on top, which is 1, and the cube root of 27 at the bottom, which is 3. So the answer is x equals to 1/3. Not plus or minus because it's a cube root. And that is our answer. You can check it and you will see that it works out to be just that. Now, let's talk about solving logarithmic equations where there are more than one logs floating around. So if the log is in more than one term, use the logarithmic properties to condense them. Then rewrite the logarithmic equation in exponential form or use the one-to-one property, and then solve for the variable. Always check, always check your answer. So here's an example. Log base 4 of x plus log base 4 of x minus 3 is equal to 1. So we have two logs here, and they have the same base. So we can combine them by using the product property. So log base 4 of x plus log base 4 of x minus 3 is just log base 4 of the quantity x times x minus 3. Now that I have that, I'm kind of stuck because I need to get x by itself. I just rewrite this as exponential form. So we have x times x minus 3 is equal to 4 to the power 1. And then I solve that quadratic equation. So this is the equation we just got. We solve the equation for x, distribute the x. We have a quadratic equation. We can solve it by one of those methods from quadratic approaches. My preference is factoring. So we end up with x minus 4 times x plus 1. And those are two possible values for x. And then, of course, after we get our answers for x, we need to check them in the original equation. To see. We try 4. When we try 4, we get log base 4 of 4, which is 1, plus log base 4 of 1, which is 0, because 4 minus 3 is 0. And that will just give us 1 plus 0, which is 1. So 4 works. But when I try x equal to negative 1, I get log base 4 of negative 1 equal to log base plus log base 4 of negative 4. Neither of those is legal. So we have to throw out x equal to negative 1 as a possible solution because that gives us something that does not work. So our only solution then is x equal to 4. So let's try a few of those questions here, and then we will move on to the next topic. Okay, so we have log base 2 of 2 log base 3 of x plus 4 minus log base 3 of 9 is equal to 2. So let's proceed with this one. This, you would think we could just combine the logs and move on, but there's actually an easier process here. If you recognize log base 3 of 9 means 3 to what power gives you 9, and that power is 2. So log base 3 of 9 is 2. So I can just simplify that to say this is log base 3 of x plus 4 minus 2 equals to 2. And then that gives me 2 log base 3 of x plus 4 equal to 4, which I will then say that if I divide both sides by 2, I get log base 3 of x plus 4 is equal to 2. And then I can rewrite that as exponential form. So 3 squared is equal to x plus 4, which means x plus 4 equals to 9, which means x plus 4 equals to 9, which means x is equal to 5. So my correct answer here is 5. Let's check that. You plug in 5 for x here, you get log base 3 of 5 plus 4 is 9, log base 3 of 9 is 2, 2 squared is 4. Oh, sorry, 2 times 2 is 4, and then minus another 2 here. 4 minus 2 is 2, so that worked. In this case, and I don't know if I'll have the space to do all of this, so we just may have to create a new page for this afterwards. In this case, we want to combine these two logarithms. So what I'm going to do is I'm going to subtract this logarithm from both sides. So I end up with log base 10, because there's no base written, of 2x plus 1 minus log of x minus 2, and that is equal to 1. So we have a log minus a log, so we can combine those as log base 10 of the quantity 2x plus 1 over x minus 2. The log with a negative in front, that goes to the denominator of the input. Now remember that this is actually log base 10. If there's no base written, it's base 10. So I can then rewrite this expression as 10 to the power 1 is equal to the input 2x plus 1 over x minus 2. I can then solve this equation by multiplying both sides by the denominator, or some people say cross multiplying. So when I multiply both sides by the denominator on the right, I end up with 10 times x minus 2 is equal to 2x plus 1. I distribute the parentheses, and this is a simple linear equation which I will just write the answer to. We subtract 2x from both sides and add 20 to both sides, so you get 8x equal to 21, so x is equal to 21 over 8. Now let's check to see if we're correct. We do 2 times 21 over 8 is 21 over 4, and 21 over 4 plus 1, 21 over 4 plus 1 will give us basically 6.25, which is 25 over 4. And then on the right hand side here, 21 over 8 minus 2 is 0.625. So if you were to do that little check on the calculator here, you will see that the left side works out to the log of 25 over 4, and the right side is 1 plus the log of 0.625. If you do those checks, you will see that they work out to be the same thing. I'm going to show you that right now on my calculator here. So let's see what we have here. So we're plugging in 21 over 8, so I do log 2 times 21 over 8, close parentheses, plus 1, close parentheses, and that works out to be that number. Then the right side I do 1 plus the log of 21 over 8 minus 2, 21 over 8 minus 2, and then we close parentheses and see what we get. We get exactly the same answer on both sides. So that was the correct result. Now let's go on to the next example here. We are going to, let me just create a little barrier for ease of reading. So we did check this and it worked out to be correct. So I'll just put that in a little box here. Now for this question here, we're going to be, this is an ln. So ln of x plus ln of x plus 2 is equal to 4. So we have 2 here. So we do ln of x times x plus 2, because here we have 2 logs with the same base equals to 4. Then that means x times x plus 2 is equal to 4. And that means x squared, not equal to 4, is equal to e to the 4, because ln is base e. So x squared plus 2x is equal to e to the 4. Now this one here, we are going to have to do, we cannot get an exact answer for this one because of the nature of exponential of the number e. So what we're going to have to do for this one, and I'll just continue this on another slide, we're going to have to write the approximate value for this and use the quadratic formula. So we have x squared plus 2x minus, and then I'm going to do e to the 4 on my calculator. So what I do is second function ln e to the power 4, and that gives me 54.59815. 54.59815, and that's an approximation. So then we use the quadratic formula, x equal to negative b plus or minus the square root of b squared minus 4 times a times c, negative 54.59815. Again, approximate values over 2 times a. Let me just pause here a minute and just allow myself some more space. Now, once we do that, we can then say, oh, let's just work this out. So I'm going to go to my trusty little calculator, and we're going to do that on that question there. Now, again, we have to do approximate values because exact values are basically impossible for us to get here easily. So we go to I'm going to do a little bit something a little bit different here. So do fraction, negative 2 plus the square root of 2 squared minus 4 times negative 54.59815, or I could just say of e to the 4, close parentheses, all of that divided by 2. And let me just go back up here a bit and just make a little adjustment. Just for the sake of precision, I'm going to delete this and write e to the power 4. That way, we know we're going to get the exact answer. Well, as close to as an answer as we should get. So then we see x is 6.456. So x is approximately equal to 6.456. Or x is approximately equal to, and let's see what happens if we change that plus to a minus. So I'm going to go back to my same expression here, but instead of doing a minus, I'm going to do a plus. Sorry, instead of doing a plus, I'm going to do a minus. And then that gives me negative 8.456. Now, I'm going to just make a little adjustment here and write that as times e to the 4. All right, and I will just erase this portion so that we don't have any confusion in the notes. And that's that. Now we know that this answer will not work because if you try to plug a negative into a logarithm, that gives you no solution. This one should work, so you can always check that answer. So we check it by doing ln of whatever answer. Well, let me clear something here. I'm going to go back up to my answer here, and I'm going to do ln of my answer, plus ln of my answer plus 2. The answer worked out to be 4, and that was what we expected. All right, we have 4 more examples to do, so we're going to do those now. I'm going to just copy this page, and we can come back to those other 3 questions in a minute. All right, so let's see if we can do this next question here. And if there's no space, we'll just fit the other one on the other side, which we're probably going to do. So for number 26, we are going to use the same properties of logarithms, and we realize that it's a subtraction, so we just do a division of the inputs. ln of x plus 1 over x is equal to 2. And then if you know that ln is log base e, then you can say e squared is equal to x plus 1 over x. Solving for x, we get e squared times x by multiplying x to both sides, x plus 1. So we have e squared x minus x is equal to 1. And then if you factor out an x, you get e squared minus 1 equal to 1. So our answer is x is equal to 1 over e squared minus 1, which is approximately equal to 1 over e squared minus 1. 0.1565. 0.1565. And all we have to do is just check to see if our answer makes sense. ln of 0.1565 plus 1 minus ln of 0.1565. And this is not going to be exactly 2 if it's correct. It's just going to be a close number because of the rounding. So that's our answer for that question right there. Let's use a little algebra rules there. Now, for this one looks a little complicated, but I bet you it's a little easier because of the base. Same rules as before, incidentally. We're going to combine the logarithms. So we have log base 3 of, since we're adding logarithms, we multiply the inputs, x plus 1 times x plus 4 equal to 2. And then we rewrite the logarithms as exponential since we can't do anything else to isolate the x. I'm going to do that, and we have x plus 1 times x plus 4 is equal to 3 squared. That's a quadratic equation. We'll have to distribute this side. That gives us x squared plus 5x plus 4, and the right side is 9. So we have x squared plus 5x minus 5, which is equal to 0. So with this one here, and I think if you try to do this one by factoring, you'll get stuck because the discriminant is not a perfect square. So we will have to solve this equation by using the quadratic formula. So we have x is equal to negative b plus or minus the square root of b squared minus 4 times a times c divided by 2a. So just to recap what we just did here, what we did was we first combined the two logarithms. We combined the two logarithms as one, log base 3 of x plus 1 times x plus 4 is equal to 2. Then we rewrote the logarithm as an exponential. The base is 3. 3 to the power 2 is equal to the inputs. That's a quadratic equation, so I worked out 3 squared to be 9. I distributed parentheses, x times x is x squared, x times 4 is 4x, plus another 1x is 5x, 1 times 4 is 4. And then I solved the equation by getting everything equal to 0. So x squared plus 5x minus 5, because I subtract 9 from both sides. And then now I just worked out the values here. So I end up with x is equal to negative 5 plus or minus the square root of 25 plus 20 is 45. That's over 2. So if we check that out on the calculator, so we have okay, let me just clear my screen so we can see more clearly what I'm doing here. So we have negative 5 plus square root 45. That divided by 2. And that gives us 0.8541, sorry. And if I do the same thing with the minus, I get a negative 5.854. So checking my answers here, I get x is equal to approximately equal to 0.8541, 0.8541, or x is approximately equal to negative 5.8541. And as you can see here, one of the answers is a negative. If you try to plug that negative into these parentheses, you will get a negative input for a logarithm, and that doesn't work. I'm going to leave you to check for the other answer here. And so we're going to move on to the last two examples in this exercise set, and then continuing with the rest of the concepts in this topic. All right, so let's take a look at this example here. I've cleaned up the page so that we can continue here. So we have two logs with the same base, and we can combine those two logs with the same base. So we have log base 1/3, and it's a minus, so we're going to do input of the log that's positive over input of the log that's negative. And then the output is -1. We rewrite this as an exponential form. 1/3 to the -1 is equal to x squared plus x over x squared minus x. 1/3 to the -1 is just 3, so we have x squared plus x over x squared minus x. And I could factor out an x and cancel. As long as x is not 0 or 1, we're good to go. But let's just proceed with a longer way. We're going to multiply both sides by the denominator on the right. And then we're going to combine like terms. So we have 3x squared minus 3x is equal to x squared plus x. And then 3x squared minus x squared is 2x squared. And negative 3x plus x is negative 4x. That's equal to 0. So if I factor out 2x, now I have x minus 2. And so I have 2x is equal to 0, or x minus 2 is equal to 0. So x is either going to be equal to 0 or x is equal to 2. And we know that x is not going to be 0, because then we'll be dividing by 0. We'll be doing the logarithm of a 0 here, which is not allowed. But when I try 2, 2 squared plus 2 is 6, and 2 squared minus 2 is 2. So let's see what that gives us when we try to work that out. So we're going to do log of 6, that's 2 squared is 4 plus 2 is 6, over log of 1/3, because I'm doing the change of base formula, minus log of 2 squared is 4 minus 2 is 2, of 2 over log of 1/3. Change of base formula. That gives me -1. So it turns out that 2 works. So we have, this is a correct solution. So that 0 didn't work. We only got one solution. So please remember to check all your solutions. Let's go through this one here. We have 2 logs on the left and 2 logs on the right hand side. Instead of putting all the logs on the same side, what we're going to do is combine the logs on each side, since there are no coefficients or no other numbers floating around. So we have log base A of x minus 1 over x plus 6 is equal to log base A of x minus 2 over x plus 3. Cross multiplying, setting them equal to each other since the bases are the same. Inputs are the same then. So we have x minus 1 over x plus 6 is equal to x minus 2 over x plus 3. And right away we realize that x is not going to be allowed to be either -6 or -3. And for that matter, if we look at this here, we'll see what we knew right away, that those two numbers are out, because then you'll be dividing by 0. So we cross multiply, we have x minus 1 times x plus 3 is equal to x minus 2 times x plus 6. We distribute the left side, we get x squared plus 3x minus x is plus 2x minus 3. And on the right hand side, we have x squared plus 6x minus 2x, that's plus 4x minus 12. Combining like terms, you'll see that if you subtract x squared from both sides, that gets cancelled. And I can then subtract 4x from both sides. And I can then add 3 to both sides. So what that will give me is -2x, because these guys canceled. And 2x minus 4 is -2x, and then the 3's canceled. So that's equal to -9. So x now is equal to +9 over 2. And of course, we can always check to see if that's right. What we're going to do is just do a cursor pass over here. We're going to say, okay, is this positive? 9 over 2 minus 1? Yes, that's positive. 9 over 2 plus 6, positive. 9 over 2 minus 2, that's positive. That's just 2.5. 9 over 2 plus 3, yes. And then you can then check it in this expression to see if inside here and inside here works out to be the same. So this will be our answer. And now let's talk a little bit about the next property here. This property is about how we solve exponential equations. How do we solve exponential equations? So I'm just gonna proceed here. So let's take a look at this one. First rule is just like the rule we just used, the one-to-one property. If you have two numbers with the same base, positive number other than 1 is the base. If the results are equal, then the inputs must be the same. So if the expressions are equal with the same base, then the exponents must be the same. It's the one-to-one property. So as long as we can get two exponential equations to have the same base, we're good to go. For example, in this case, we can write this as it is, 6 to the x minus 3 over 4, but the square root of 6 is just 6 to the 1/2. Since the bases are the same here, we can just say, oh, that means x minus 3 over 4 is equal to half. And then I can just solve. X minus 3, multiply both sides by 4, we get 2. So that means x is equal to 5. Then you can always check the solution here. 5 minus 3 is 2. 2 over 4 is half. 6 to the half is the square root of 6. So that does work. In this case, 8 raised to what power gives you 16? It's not 2 because 8 squared is 64. So that's a little tricky. I could use a smaller base, a number that when I raise it to a certain power, I get 8. And when I raise that number to another power, I get 16. 4 doesn't work because 4, well, it gives a more tedious result. 4 to the 3/2 is 8, but that's kind of messy. But if we do 2, that's better. So 2 cubed is 8. So I'll replace 8 with 2 cubed, and I'll put x plus 3 in parentheses here. And then 2 to the 4 is 16. And I'll put the x minus 1 in parentheses here. And then we distribute, well, we'll get 2 to the 3 times x plus 3, that's the exponent rule. And 2 to the 4 times x minus 1, exponent rules again. The bases are the same, so the inputs must be equal. So I will just continue over here as 3 times x plus 3 is equal to 4 times x minus 1. I distribute the parentheses, I get 3x plus 9 is equal to 4x minus 4. So then I can just solve. I can just subtract 3x from both sides and add 4 to both sides. And that will give me 13 is equal to x. So x is equal to 13. And we can always check these. They may give us somewhat big numbers here. I plug in 13 for x here. I get 13 plus 3 is 16. 8 to the 16 is equal to 16 to the 12. So let's check those both. Hopefully the calculator can hold all the answers. So 8 to the power 16. Eight to the power 16 is pretty large number, and 16 to the power 12. Same large number. Well, so that gives us an idea of what we're working with. So let's continue with an example here. 4 to the x equal to 1 over 8. I simply replace the bases with the same base, which in this case is again 2. 2 squared is 4, and 2 to the 3 is 8. So 2 to the negative 3 is 1 over 8. And then this means 2 to the 2x is 2 to the negative 3. Set the exponents equal to each other. We're not canceling, by the way. We're simply setting the exponents equal to each other, and we're solving. And then, of course, we can always plug them in to see if they work. 4 to the negative 3 over 2. If you plug that into your calculator, you'll get the same answer on both sides, 1 over 8. Now, that said, we can now talk about the using logarithms to solve exponential equations. This is going to be a lot more involved. The first basic step is if you only have one exponential expression, that means one expression with an exponent and the other one is not. We simply isolate the exponential equation and then take the log of both sides and solve. So let's take a quick look at an example here. And this example, we're going to use e. And with e, the log base e is ln. So if you have e, you want to bias yourself towards ln because it may make your life simpler. But other than that, we'll just use whichever log we prefer, log base 10 or ln, which is log base e. Just remember, ln of e is 1, or ln of e to the x is x. Log of 10 to the x is x because of the inverse property. So let's start off here. What we're going to do is isolate the variable by removing the weakest link, reverse PEMDAS. So I subtract 2 from both sides and divide by 3. And now the e is by itself to an exponent. I'm stuck with the variable in the exponent, so I take the natural log of both sides. So I take the natural log of both sides, and then that exponent can now become a coefficient. The ln will cancel the e actually, and we have ln of 4/3. And then I just solve for x, add 1 to both sides, and then divide by 2. I can plug that into the calculator, and I get this quantity here. Please remember to use your parentheses properly when you're doing your calculator operation. So let's take a quick look at a few examples here, and then we will move on. So for this one, the first thing I will do is isolate the exponential so that we can try to get the x by itself. So I'm going to divide both sides by 4. So I'm going to divide the left side by 4 and the right side by 4. That's going to give me a decimal, not a big deal. That's why we have calculators. So we end up with 2,568, sorry, 0.25. And then since that's an e, I just take the natural log of both sides. Ln of e to the 7x is equal to ln of 2568.25. The ln cancels with the e, leaving 7x is equal to ln of 2568.25. And then I divide both sides by 7, so I get x is equal to the natural log of 2568.25 divided by 7. That's going to be approximately equal to, let's do that on the calculator here. So we do ln, and it opens parentheses first, 2568.25, close parentheses, divide by 7. And that gives us 1.121569. So 1.12157. 1.12157. So that means x is approximately equal to 1.122. Just three decimal places. And that's that. So this is the exact answer, and that's the approximate answer. With this one, similar approach. Let's just create a little divider here. We take the natural log of both sides, ln of e to the 1 minus 8x. And that gives me ln of 7957. So the ln and the e undo each other, they cancel. And we end up with 1 minus 8x is equal to ln of 7957. I can subtract 1 from both sides and then divide by -8. Or I could move the 8x to the left side and then subtract that from 1. Either way, I would end up with x is equal to ln of 7957 minus 1 divided by -8. And then we can do work that out on the calculator. So let's do that now. ln 7957 close parentheses minus 1, and then I'm going to divide that quantity by -8. negative 0.997726, negative 0.997726. So x is approximately equal to negative 0.998. We can always check that out on the calculator. We do e to the power 1 minus 8 times negative 0.998. It's not going to give us the exact answer, but it should give us something reasonably close, 7974.46. Now, if I were to do the same thing, but with the bigger answer, 997726, then I would get a much closer answer right there. All right, so let's take a look at the next example. In this case, we have to get rid of the 7 first, so I'm going to add 7 to both sides. So I have e to the 4x minus 5 is equal to, we add 7 to this, we get 11,250. And then I'm going to take the natural log of both sides because the variable is in the exponent of e. And then natural log will undo the e. So we end up with 4x minus 5 is equal to the natural log of 11250. So then I proceed with adding 5 to both sides and then dividing by 4. So that will give me my exact answer and then my approximate answer, which you can check in on your calculator. I'm just going to give you, well, let's just do that right now. So open parentheses for the numerator, 5 plus the natural log of 11250, close parentheses, and then close parentheses for the numerator, divided by 4. 3.582. And I'll leave you to check that answer. Now, these last two examples I have at the bottom here, they look different from what we've been doing because you have two different bases, well, same base with different exponents, and then there's an additional number there. So that one those look a little weird. So how are we going to approach those? In reality, these are actually quadratic equations. They are disguised quadratic equation. So they will require a little bit more thinking and work. So I'd like you to just pause the video if you can and try to see if you can figure out what the approach is. And then you can come back and see my explanation as to how to approach this. Okay, now, so let's take a look at how we approach this. One of the things you need to remember here is that e to the 2x is really the square of e to the x. So if I let's say m is equal to e to the x, that would mean m squared is equal to the e to the 2x, cos e to the x squared. And so then we can realize then that I can replace e to the 2x with m squared and replace e to the x with m. And what I have there is a nice quadratic equation which I can now solve easily. In this case by factoring two numbers that multiply to be -3 and add to be +2 are -3 and +1. So I end up with m equal to -1 or m is equal to 3. Now, once I have those values for m was just a stand-in to make this a little simpler to see. So really what I'm going to do is say, oh, m was e to the x. E to the x is equal to -1, or e to the x is equal to 3. The thing is, exponential functions do not give you negative outputs. They only give you positive outputs because of the properties of exponential functions. So that one's out. So then how do I get this one? I just take the natural log of both sides and then cancel the ln and the e, and we end up with x is equal to the natural log of 3, and that's our answer. And we can check it. E to the 2 times the natural log of 3 would be 9. E to the natural log of 3 is 3. 2 times 3 is 6. So 9 minus 6 is 3. Minus 3 is 0. Or you can just plug it into your calculator to check. So now I'd like you to try this question, number 5, using a similar approach. And then you can always check to see if your answer is the same as mine when I go through it here. All right, so let's take a look at what we do here. We say, oh, well, if you notice here with this one, it's e to the 4x and e to the 2x. So if I let m equal to this guy, e to the 2x, then that would mean m squared would be e to the 4x, because that would be e to the 2x squared, which is e to the 4x. Which means I can then write this as m squared minus 3m minus 18. And then I can solve this as I did before by factoring. I need two numbers that multiply to be -18 and add up to be -3. Those numbers would be +3 and -6. So that would mean m is equal to -3 or m is equal to +6. So resubstitution, we see then that e is either e to the 2x this time is equal to -3, or e to the 2x is equal to 6. Again, exponential functions do not give you a negative output, so we can then proceed with the other part by taking the natural log of e to the 2x and the natural log of 6. Ln and e will cancel, so you'll end up with 2x equals ln of 6. So that means x is equal to the natural log of 6 over 2. And I'll leave you to check that answer on your own. Now let's talk about solving equations that cannot be written this simply. So let's see if we can get into that concept right now. Now we'll talk about the steps for solving an exponential equation. And if you have an equation with two exponential portions, that means a number raised to a power and another number raised to a power, we can solve those by using logarithms. We'll just take the log of both sides, either the natural log or the common log of both sides, and then we'll use the power property to move the exponents to the coefficient of the logarithms, and then we'll solve for the variable using basic algebra. Here's an example. 2 to the x minus 1 is equal to 5 to the 2x plus 3. As you can see, there's no easy way to get these two numbers to have the same base, but it's very hard to isolate a variable because the variable is in two different exponents. So what we do is we take the logarithm of both sides. In this case, we're using natural log. So we're going to take the natural log of both sides, and that allows us now to move the coefficients to the exponents to become coefficients. Please remember to put those exponents in parentheses. So we put the x minus 1 in parentheses and the 2x plus 3 in parentheses. And then we solve the equation. We distribute the parentheses on both sides and then combine like terms. So this is just a continuation of where we left off here. So we distributed the parentheses, and now we're going to combine like terms. We're going to put the x's together. So I'm going to move the minus 2x ln 5, move the 2x ln 5 to the left side and the ln 2 to the right side by subtracting appropriately and adding. And then I'll factor out the x here and then divide by the coefficient, the thing in parentheses, and that is my exact answer, which I can then plug into the calculator to get negative 2.186, which you can then check to see on your calculator to see they give you approximately the same answer. It's rounded, so the answer will not be precise or exact. So remember to use your parentheses for those. Let us do a few examples to illustrate our point here. So for this question here, very simply, as before, we simply take the natural log of both sides or the log, but I'll use, my preference is natural log, so I'm going to use that. So you do ln of 8 to the negative x is equal to ln of 1.2. And then you move the negative x to the coefficient. So you end up with negative x ln of 8 is equal to ln of 1.2. And then if you divide both sides by negative ln 8, you get ln of 1.2 over negative ln of 8. And we can always work out an approximate value for that. So ln of 1.2, close parentheses, divide by negative ln of 8, close parentheses, equals negative 0.0876. So 3 decimal places, negative 0.088. Just approximate. And just a reminder, see 0.0876. And I'll leave you to check that answer. Let's move on to the next one. In this case, we want to isolate there's only one expression with an exponent, so that's relatively easy to do. We divide both sides by 0.3, so I end up with 4 to the power 0.2x is equal to 0.2 divided by 0.3, which is 2/3. Leave it like that for now. And then I'm going to take the log of both sides just to show that it's the same process. But my preference, as I said, is typically to use ln, unless the base is base 10. And then, of course, the coefficient, the exponent becomes the coefficient. So we have 0.2x log 4 is equal to log of 2/3. All right, I'm going to need some space here, so I'll create a little extra space for myself here. Then I divide both sides by 0.2 log 4, so x is equal to log of 2/3 over 0.2 log 4. Let's see how we do that on the calculator here. So log 2/3 divided by the parentheses 0.2 log 4, close parentheses and close the denominator, negative 1.462, negative 1.462. And let's just check that one to make sure that we are correct here. So we do let me clear this, 0.3 times 4 to the power 0.2 times negative 1 0.462, close parentheses, and close parentheses, and the answer for that is approximately 0.2, approximately 0.2. So let's continue with the next examples here. Let's see if we have space. This one, it's 2 to the x plus 1 is equal to 5 to the 1 minus 2x. Two different bases. What I'm going to do is take the natural log of both sides. 2 to the x plus 1. I'm going to put that in parentheses. And ln of 5 to the 1 minus 2x. I move the parentheses, the exponents to the coefficient. I have x plus 1 times the ln of 2 is equal to 1 minus 2x times the ln of 5. And then we can proceed with the distributive property and simplifying. We have x times ln of 2 plus ln of 2 equal to ln of 5 minus 2x ln 5. Move the 2x ln 5 to the left side and the ln 2 to the right side. We have x ln of 2 plus 2x ln of 5 is equal to ln of 5 minus ln of 2. And I'm going to proceed a little more here. So we end up with x times ln of 2 plus 2 ln 5 equal to ln of 5 minus ln 2. So x is equal to ln 5 minus ln 2 over ln 2 plus 2 ln 5. And then we can just check that out on the calculator. Approximately equal to open parentheses ln 5 close parentheses minus ln 2 close parentheses close exponent the parentheses for the numerator, open parentheses for the denominator, ln 2 minus 2 plus 2 ln 5. 0.234. So the answer for this is approximately 0.234. And let's check this one quickly. This time I'm just going to use the answer button here to see what we have. So we have 2 to the power answer plus 1 equal, and then see what that equals. And then 5, let's go back to the up here. Use the same answer here. 5 to the power 1 minus 2 times the answer is same result. So we did do the right thing. All right. Now I'm going to need some space for some of these questions. So what I will do is create a duplicate of this page and continue with those questions on the next page. All right, so let's continue with these questions here. Let's see, with this one, it's the same as before. It's just that we have a fraction. Fractions are not that scary if you approach them the same way as you do other numbers. So we're going to do the same thing as we did before. I'm going to use the natural log again in this case because it is my preference to use over the log. It's neater to write as well. So we have the natural log of 4/3 to the 1 minus x equals to the natural log of 5 to the x. You move the 1 minus x and the x as coefficients. So if ln of 4/3 equals to x ln 5, and then I distribute, I get ln of 4/3 minus x ln 4/3 equal to x ln 5. So ln of 4/3 is equal to x ln 5 plus x ln 4/3. So ln of 4/3 is equal to x times ln 5 plus ln 4/3. And I actually am going to combine those two fractions together, those two logarithms together, just for the sake of looking a little neater. So ln of 4/3 is equal to x ln of 5 times 4 is 20 over 3. And then x is equal to ln of 4/3 over ln of 20/3. We can work that out on the calculator. Remember the parentheses. So we do ln of 4/3 divided by ln of 20/3. Point 1516. So our answer here is approximately 0.152. 3 decimal places. All right. Let's continue doing a few more examples here. And let's try this one here and this one, and then see what we can do from there. So we have a few decimals here, nothing to worry about. We take the natural log of both sides again. Ln of 0.3 to the 1 plus x equals to ln of 1.7 to the 2x minus 1. So the exponents become coefficients. And then we distribute. So we have ln of 0.3 plus x ln of 0.3 is equal to 2x let's make a little adjustment here. 2x ln 1.7 minus ln 1.7. And then I'll move things around. I have ln of 0.3 plus ln of 1.7 is equal to 2x ln 1.7 minus x ln 3. I can combine these two together. I'll just call that ln of 0.3 times 1.7, and 3 times 17 is 51, so this should be 0.51. 0.3 times 1.7 0.7 is 0.51. So ln of 0.51 equal to x times 2 ln 1.7 minus ln 3. So x is equal to ln of 0.51 over 2 ln 1.7 minus ln 3. So let's see what that works out to be. ln of 0.51 divided by parentheses 2 ln 1.7, close the parentheses for the ln, minus ln 0.3. I said 3, so I need to make that correction there. And that will give us negative 0.297. Negative 0.297. And of course, we check using the calculator again. So let's clear this out and check our answers. 0.3 to the power 1 plus negative 0.297. And then 1.7 to the power 2 times negative 0.297 minus 1. And both answers work out to be approximately the same. We're rounded, so they're not going to be exactly the same. So that indicates that we did the right process and we are correct to the correct number of this precision. So let's wrap up here with, wrap up this page with these examples. We have a number of others, and I recommend that you try a lot of these examples on your own, and then you can check. The rest of this video, the rest of this lesson is basically exercises being done. So if you're comfortable, feel free to move on to do other things, but it's important to try these. So let's look at this one here. In this case, taking the natural log is the best bet overall because we have one of the bases is e, and natural log undoes e, leaving just the exponent x plus 3. And then this x goes to the front, x ln pi. We subtract x from both sides, we get 3 equal to x ln pi minus x. And so I get 3 is equal to x times ln of pi minus 1. And so that will give us x is equal to 3 over ln of pi minus 1. And that is the exact answer. We can get the approximate answer by using our calculator. So we have 3 divided by parentheses ln pi close parentheses minus 1. 20.728. 20.728. And that's our approximate answer for that one. I leave you to work on that on your own. So let's move on. So I did these questions, so we can clear those out. Okay, I'm having a little difficulty here, so let's try this again. All right, now let's try these more complicated looking questions. And let's see what we can accomplish with this. So for this first question here, it's like what we did earlier. This guy's quadratic. So let's say we let m equal to 3 to the x. That would mean m squared is 3 to the x squared, which is 3 to the 2x. So we have m squared plus m minus 2 is equal to 0. We factor, we get m plus 2 times m minus 1. So that will mean m is equal to negative 2 or m is equal to 1. That would mean 3 to the x is equal to negative 2 or 3 to the x is equal to 1. This does not give you a number. And 3 to the x equal to 1 means that 3 to the what power gives you 1? That's 3 to the 0. You can also just take the natural log of both sides. You get 3 to the 0, ln of 1 is 0, so x ln 3 equals to 0, so x is equal to 0, and that's your answer right there. 3 to the 0 plus 3 to the 0 is 1 plus 1, which is 2, minus 2 is 0, so it did work. Let's press on to the next question here. And this next question looks a little different because now you don't have the same base. But what we do recognize here is that 9 is actually 3 squared. So this is 3 squared to the x minus 3 to the x. And if you notice here is 3 to the x plus 1 is actually 3 to the x times 3 to the 1. So I'm going to write it this way, 3 to the 1 x times 3 to the 1. And it's probably still not clear here, but this is 3 to the 2x minus 3 times 3 to the x plus 1. And then if I let m equal to 3 to the x, which would mean m squared would be 3 to the 2x, we'll have m squared minus 3m plus 1 equal to 0. This one cannot be factored, so we have to use the quadratic formula. M is equal to negative b plus or minus square root of b squared minus 4ac divided by 2a. So that means m is equal to 3 plus or minus the square root of 5 over 2. You will see that both of these answers actually work. So I'm going to leave you to check the answers to this one, and we'll move on. So if you were to do number 55, you'll just think about it in the similar way. We'll recognize that 5 squared is 25. So 25 to the x is 5 squared to the x. And we can just say that this then can be written as let m equals to 5 to the x. So this would be 5 to the 2x. So we have m squared would be 5 to the 2x. So we have m squared minus 8m plus 16 equal to 0. You can see that's factors to be m minus 4 times m minus 4, which means m has to be equal to 4. So that means 5 to the x is equal to 4. And that would mean that if we take the natural log of both sides, you get ln of 5 to the x is equal to ln of 4, which means x ln 5 equal to ln 4. And that leaves us with x is equal to ln 5 over ln 4. I will leave that as an exact answer. You can check the decimal version of that. Now for the last two on this page, we have, in this case, again, 49 is 7 squared. So now we can see that it's 2 times 7 to the 2x plus 11 times 7 to the x plus 5 equal to 0. So if I let m equals to 7 to the x, that would mean m squared is equal to 7 to the 2x. So that would mean 2m squared plus 11m plus 5 is equal to 0. And if we're going to try to do factoring with this one, we can probably factor by grouping. You'll get two numbers that multiply to be 10 and add to be 11. That's 1 and 10. So then I can just factor this by grouping, and I'll leave you to work out the details of this factoring. So what we have here now is that so we have m is equal to 5, or m is equal to negative 5, or m is equal to negative half. And that would mean 7 to the x is equal to negative 5, or 7 to the x is equal to negative half. That is impossible, because there is no positive number raised to a power that will give you a negative result. And you could see here, if you plug in any number here and you're adding the results, each of these terms will give you a positive answer. So they will never add up to be 0. So there's actually no solution for that one. All right, the last one on this page. Let's see how we can approach this one here. And with this one, we see that both of them have a 4 to the x. So we can rewrite these as 4 to the x minus 10 over 4 to the x is equal to 3. And if I multiply both, or if I let m equal to 4 to the x, then I'll have m minus 10 over m is equal to 3. Multiply all sides by m, I get m squared minus 10 equal to 3m. And then solving that quadratic equation, I end up with m plus 2 times m minus 5 is equal to 0. So m is equal to negative 2, or m is equal to 5, in which case 4 to the x is equal to negative 2, or 4 to the x is equal to 5. And this part here is impossible. And just for the sake of space, I'll leave you to work out that x is equal to let me just make a quick correction for this one here, because I just realized that I rushed here. This is ln 5 over ln 4. And there we have it. We have a few more challenging questions here we're going to do, so let's try those right now. All right, so let's do these questions here to see how many of them we can get through. Log base 2 of 3x plus 2 minus log base 4 of x equal to 3. So we have, if you notice, the bases are different. So we have a little challenge here. But if we can change both of them to base 2, that will work. So I'm going to leave this as log base 2 of 3x plus 2. And then I'm going to write this as log base 2 of x over log base 2 of 4. Now, these things come by practice, so I don't expect that you will recognize this process right away. But this shows how versatile and how many different approaches you can have to using the properties of logarithms to solve equations. Now, log base 2 of 4 is 2, so basically this is 1/2 log base 2 of x. And then I can combine those. I can combine the logarithms after I move the coefficient of x to the exponent. So I have log base 2 of x to the half equal to 3. And so I have log base 2 of x of 3x plus 2 over square root of x is equal to 3. And I'll just move some of these guys over for space. And then that would mean 2 to the 3 is equal to 3x plus 2 over the square root of x. We just rewrite it. So I multiply both sides by 8. By square root of x, I get 8 square root of x is equal to 3x plus 2. And now, since I want to find the square root, I have to square both sides. So I get 64x is equal to 3x plus 2 squared. Let me put it this way. 8 square root of x squared. So 64x is equal to 9x squared plus 12x plus 4. And that's a quadratic equation. So we have 9x squared plus, 12x minus 64x is 52x, negative 52x plus 4. And then we can solve that equation by using the quadratic formula. I'm going to just move a few things around here. So solving this using the quadratic formula, we have x, that's equal to 0. So x is equal to negative b plus or minus the square root of b squared minus 4 times a times c divided by 2a. So let's see what that works out to be. Negative 52 squared minus 4 times 9 times another 4. 2560. So that leaves us with 52 plus or minus the square root of 2560 over 18. And that means x is equal to 52 plus or minus 16 square root 10 over 18. And I leave you to work that out to see what that works out to be. And as you can see, when we work out square root of 2560, it's smaller than 52. So all the answers here are going to be positive. And so you can check the answers. So I'll just leave here, check answers. Because we may still have extraneous solutions. So moving on. In this case, We have log base 16 of x plus log base 4 of x plus log base 2 of x equal to 7. Just as we did in the last case, we're going to go with the smallest base since it's relatively easy to write the other numbers in terms of that base. So we're going to write this guy in terms of base 2. So I'm going to write this as log base 2 of x over log base 2 of 16 plus log base 2 of x over log base 2 of 4. And then plus log base 2 of x equal to 7. Now, this here is 4 and that's 2. So really I'm doing a 1/4 log base 2 of x plus half log base 2 of x plus log base 2 of x is equal to 7. Multiply all sides by 4 to get rid of the fractions. I get log base 2 of x plus 2 log base 2 of x plus 4 log base 2 of x is equal to 28. Combining the logarithms now, I get log base 2 of x times x squared times x to the 4. I combine two steps together here, and that's equal to 28. And then finally, well, not finally, putting the logarithm, rewriting the logarithm as an exponential, we get 2 to the 28 is equal to x to the 1 plus 2 plus 4 is 7. So when we take the 7th root of both sides, we get 7th root, well, let me show it another way. I'm going to divide both exponents of both sides by 7. Okay, 7th root of 2 to the 28 equal to 7th root of x to the 7. So we get 2 to the 4 equal to x, so x is equal to 16. And we can always check. Log base 16 of 16 is 1, log base 4 of 16 is 2, and log base 2 of 16 is 4. 1 plus 2 plus 4 is 7. And that is the correct answer for that question there. So these questions are forcing us to think outside of our usual box. So we'll go on to the next questions in a few moments. Okay, let's continue here with these additional questions. Let's clear a little path here for some work here. Now this one looks a little tedious as the others have, but if we use the rules of exponents, we can work this one out relatively quickly. We just recognize that cube root of 2 is 2 to the 1/3. And all we're doing is using the fact that if the bases are the same, then the exponents are equal. So I do 2 to the 1/3 times 2 minus x is equal to 2 to the x squared. So since the bases are the same, we have 1/3 times 2 minus x is equal to x squared. If I multiply both sides by 3, I get 2 minus x is equal to 3x squared. And then I have a quadratic equation. So I can just say 0 is equal to 3x squared plus x minus 2. And if we do a little factoring here, we get 3x squared. It needs two numbers that multiply to be -6 and add up to be 1 are 3x minus 2x. And then if you factor by grouping, you'll see that the answer works out to be x plus 1 times 3x minus 2. So that means x is equal to -1 or x is equal to 2/3. And we can check those relatively easily. If you use -1 for x here, you get 2 minus 2. 2 minus -1 is 3. Cube root of 2 cubed is just 2, and 2 to the 1 squared is 2, so that works. If you use 2/3, a little trickier. 2 minus 2/3 is 4/3, and the cube root of 2 raised to the 4/3 is the same as 2 raised to the 4/9. And if you do 2/3 cube squared, you get 4/9. So both of these answers actually do work. Let's move on to the next examples here. We have log base 2 of x till log base 2 of x equal 4. Now that one looks tedious, but isn't actually quite as tedious as it appears. So let's see if we can recognize a few things here. The power rule for logarithms says that if the exponent of the input is raised to a power, then that power can now become the coefficient. So I'm going to do that right now. I'm going to write log base 2 of x as a coefficient of log base 2 of x. And what you'll see here is that what we have is log base 2 of x squared is equal to 4. So then we can then solve this equation by taking the square root of both sides. I'm just going to use my let me show every step here. So I do log base 2 of x squared, do the square root of that, and that's going to be the square root of 4. Well, not just the square root, plus or minus the square root of 4. So even though we cannot plug in a negative into logarithms, we can get a negative answer. So what we have here is log base 2 of x can be equal to -2, or log base 2 of x can be equal to +2. If we rearrange this, we see then that x would be equal to 2 to the -2, or x would be equal to 2 squared. So my two possible answers for x are 2 to the (1/4) or 4. And if we check that, we can see if it's correct. If x is 1/4 here, log base 2 of 1/4 is -2, and then x to the and then 1/4 to the -2 is 4 squared, which is 16, and 2 to the 16 is 2 to the 4 is 16. So that would work out fine. And if we use 4, it will also work out. So both answers work out quite nicely. You can also check it on your calculator or another means. And let's check on to the next questions here. This one looks a little challenging. So let's multiply both sides by 2 to make it a little easier to see what's going on. E to the x plus e to the -x is equal to 6. Now we have a negative x here, so if I multiply everything by e to the x, I get e to the x squared plus e to the -x times e to the x equal to 6e to the x. Now what that will do is it will combine the exponents here by adding them, and that will give me e to the 0. So I end up with e to the x squared plus e to the 0 equal to 6e to the x. And that means, and if I let m equal to e to the x, I end up with m squared plus 1 equal to 6m. And there we have m squared minus 6m plus 1 equal to 0. And that we just solve using the quadratic formula. (b plus or minus the square root of b squared minus 4 times a times c over 2a. So then m is equal to 6 plus or minus the square root of 32 over 2, which is 3 plus or minus 4 4 square root 2. I believe this is 2 square root 2. Because this is 16, it's 4 square root 2, and then divide by 2, it's 2 square root 2. And we can always check those answers. We'll just check one of the answers here. Well, I'll leave you to check those answers just because of time. Now, let's move on to, and both answers will work. Let's move on to the last example on this set. With this one, we have a base 5 and a base 3. Those don't have a nice connection, but we can just start off with ln. So change of base formula says we can rewrite this as ln of x over ln of 5 plus ln of x over ln of 3 equals to ln of 1. Now the ln of 1 is 0. And if you notice, both of these have ln of x, so we can factor out ln of x from this. We have 1 over ln of 5 plus 1 over ln of 3. And if we divide both sides by this stuff in parentheses, which I'll just indicate by 1 over ln 5 plus 1 over ln 3, and since we're dividing 0 by a non-zero quantity, then we have a simple result that remains. ln of x is equal to 0, which means e to the 0 is x, which means x is 1. And you can always check that answer. Now for these last set, we'll just do as many as we can here. If you notice, all of these for number 93 are at the same base. It can be written as base 5. So we have 5 to the 2x times 4. 2x plus 4x is 6x. And this is 5 to the 3. So all we have is 6x is equal to 3, which means x is equal to 1/2. There we go. With this one, it's very similar. We just do 3 to the x plus 2 plus x. And this is 3 to the 4. So what we have is 2x plus 2 is equal to 4, which means x is equal to 1. For this one, we solve for the ln of x, so we isolate the absolute value. So ln of absolute value of x is equal to absolute value of ln of x is equal to 3, which means ln of x is either equal to -3 or +3, which would mean x is either equal to e to the -3 or x is equal to e to the +3. Based on their definition, ln is log base 3. Similarly, if you rearrange this one, you'll see that absolute value of log of x is equal to 6 over 3, which is 2. So that means log x is equal to -2 or log x is equal to 2. Log means log base 10, so that means x is either equal to 10 to the -2 or x is equal to 10 squared. So x is equal to 1 over 100 or x is equal to 100. With this one, it's a little trickier. We can rewrite this as 3 to the x squared equal to 9. Well, let's not do it that way. Let's do the natural log of 3 to the x squared equal to the natural log of 45. Rearranging that, we get x squared ln 3 is equal to ln 45. So x squared is equal to ln of 45 over ln of 3. And that would mean x is equal to the plus or minus the square root of ln of 45 over ln of 3. And I think we can leave it like that. Number 50 is done in a similar way, so I'm going to bypass that and go on to number 101. For number 101, again, we have the same base, that we can get the same base namely base 5. So we get 5 to the 2 to the 2x. So we have 5 to the x squared minus 12 is equal to 5 to the 4x. So x squared minus 12 is equal to 4x, which means x squared minus 4x minus 12 is equal to 0, which if you can factor that to be x plus 2 times x minus 6, and then that will give you x equals to negative 2 or x equal to 6, which you can check both answers to see if they work. I'll leave you to do number 102, which is similar. Number 99. Since all of these have the same base, ln, we can combine them with the condition that we move the 2 to the exponent of x. So we have ln of 2x plus 1 in the numerator times x minus 3 in the numerator again over x squared in the denominator, and that's equal to 0, which means e to the 0 is equal to 2x plus 1 times x minus 3 over x squared. Solving this, we said this is actually 1, so you can cross multiply both sides. So you get x squared equal to 2x squared minus 3x plus x, that's minus 2x minus 3. So we have 0 is equal to x squared minus 2x minus 3. So 0 is equal to x minus 3 times x plus 1. So x is either equal to 3 or x is equal to negative 1. And what you will notice is that if you try 3, this part doesn't work. And if you try negative 1, that one doesn't work. So the answer is that there is no solution. No solution. I'm going to stop here with these examples, and I'm going to leave you to work on these on your own. Well, no, let me stop. Let me just do this one example here. So we have ln of 3. We're going to, another way to do this is to move the negatives to the other side and combine them. So we have ln of quantity x times x plus 5. I did 2 steps here. I moved the ln's to the left side, to the right side, and then I used the property of addition of logarithms to combine them. And then that would mean 3 is equal to x squared plus 5x. So then that means 0 is equal to x squared plus 5x minus 3. And then what I will do is solve this using quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4 times a times c. So 4 times 3 times 1 over 2a. So x is equal to negative 5 plus or minus square root of 37 over 2. The only answer that works would be negative 5 plus square root 37, because our answers have to all be greater than 0. So based on that, we can say that the only answer that works is negative 5 plus square root 37 over 2. Okay, this was a pretty long video, and I understand it's a bit tedious, but I wanted to give enough practice exercises for you to be able to use as examples for solving equations. Now, make sure you use Khan Academy and OpenStax, OPE, and stax.org for additional practice and for videos. And all the best. Keep practicing.